We are going to do a high-level overview of the Deckard runtime execution flow. We will look at some code. The code that we look at is just to orient a world view of the execution flow. The runtime is really not required to completely understand it to actually use the platform. So looking at this diagram, we see that there is a thing called event prompt, and that's where everything starts. So the runtime will receive event prompts. Let's not worry about where they actually come from. It's sort of irrelevant at this point. The event prompt is a payload that includes event information and prompt information. The event information with the question mark there is not required to have a valid event prompt. The prompt information is required. The runtime splits out that information, and from that, what we call it incubates a replicant. A replicant is made up of a ALF definition, and we see the ALF definition is a definition of activities a replicant can perform, and it also has a state, which is the context of which the replicant performs activities and includes what we call working memory. You can see the state actually is sort of part of the replicant and actually part of the runtime. The state itself has what we call base state, which all replicants get. That is the state of that particular reaction to an event prompt. And it can potentially have what we call long-term memories. We'll get in deeper in that in other discussions, but understand that the state is made up of a base and potential long-term memories. Those long-term memories come from a repository. Also, the repository is where the ELF definition is set, and other things like skills, tools, services. We won't get into much of that, but understand that when it looks for a ELF definition for activities, it will look at what we call the repository and cache. And from that, which that is local, either on disk or in memory to the runtime instance, or it will pull it from a repository. And that way it can cache the information, so the next time it wants to use that ALF, it won't have to always pull that down. So once a replicant performs an activity, it will come to a conclusion. That is literally and figuratively. Conclusion, that means it's concluded the activity, but also it can create a conclusion, which is an object of information. That conclusion may potentially involve a malfunction that can either happen at the replicant level or the runtime level. And a malfunction just means something went wrong during the processing of that event prompt. Once the replicant actually goes through a conclusion, there is a thing called a resolution, which comes from the runtime, and that includes a conclusion, a status, and genealogy. We'll get into the details of that. Now, this looks like a typical model of a client server, and at its heart, it is sort of, right? It does run on Lambda. It can run outside of Lambda. That said, we don't want to think of it that way. We can think of it as an event prompt is ingested by the runtime, meaning some system pushes something, an event prompt. It processes event prompts, and it emits a resolution. We don't want to think of it as returning a resolution, and we'll see why that makes sense to think of it that way. But you can see I have the event prompt and resolution connected to this called pseudo sync, meaning the whatever process emits or provides an event prompt to the runtime doesn't necessarily mean it's the same process that will receive the emitted resolution. I call it pseudo sync, and we'll see as we get deeper into the runtime. Not on this example here, and not on this training video here, but as we get deeper, it'll make sense to think of it that way. So let's look at a couple example of an event prompt and resolution. So we can see that here we have at the top a simple event prompt. The body node is the only required node, and that holds the prompt information. Here I just put an example value for an event called caller ID, which doesn't mean anything. It can whatever context that you're using for. So the event information would just be a bunch of name value pairs. Now, the reason why we have this is typically the Deckard will sit behind an API gateway, and the API gateway actually makes a whole event object that has a bunch of information in there. One being the body. That's why it's called body and not prompt, because it's dictated by the API gateway. But understand that the body node there is the only required node, and it actually is holding a stringified JSON of the prompt. Now below, I actually made it clearer to see that prompt information. You can see some details of an ALF type and meta and query. Don't worry about too much of the details here, but that's just an example. Below that, there's the schema of what a prompt would look like, required information. There's an ALF type, query, meta, and genealogy. That are the 4 nodes of a prompt. None of them are required, though you have to provide either an ALF type or a genealogy. And we'll get into how that drives how a replicant is incubated. Next, we have an example of a resolution that's emitted. The top one, you can see that there obviously was a success, right? There's a conclusion. A conclusion can be any JSON-based node value. Here we're looking at sort of as a native JavaScript object for just easy readability. A status, we won't get too much into that, but there'll always be a status returned, and we'll discuss the details of that further on. And genealogy will always come back as a genealogy with an ID, and we'll explain at some point what genealogy means. Below is an example resolution emitted that had a malfunction, and you can see the conclusion is has a malfunction object in that conclusion. So a malfunction actually is a conclusion that was propagated out through the resolution that comes back from the Deckard runtime. And we can see here this malfunction. A malfunction will always have a type, details, and a trace. This is an example type called auto exception. Auto is the depository code. The details is unable to get an object, so we can tell here that it wasn't able to get this ALF definition. And then the trace is just some more information about where that happened in the code. In this case, we can say for some reason this ALF definition doesn't exist. That means it didn't exist either in memory or cache or local to disk or in the repository. So that's how it would look for that to try to find that ALF. It first looks in memory, then looks on disk, and then looks in the depository, the repository. And so in that case, we didn't find anything. So that's an example of a resolution that's a malfunction. So let's look at some the runtime code that corresponds with the diagram that we showed. So here we can see this is the runtime, 15 lines of code. And we import the Deckard platform. We initialize it, and that's a one-time initialization. Now remember, this is designed to run a Lambda, though it can run outside Lambda, and that initialization happens once per Lambda instance. So there's reasons why they do it that way. But if we look at the actual runtime code, there are 3 steps in there. We can see that it receives an event prompt, and we incubate a replicant with that event prompt. And then we try that code, and if there's a malfunction that comes out, we catch that, and then we set the malfunction to the system with the malfunction that was caught, and then we always return a resolution. So that mirrors completely what we see in the diagram here, where event prompt comes in, A replicant, runs a activity based on its information, draws a conclusion, and he emits a resolution. So let's dig a little deeper in the code. As I mentioned, you don't need to understand this code to build solutions, but by looking at this, it kind of can help you understand the platform. So obviously, looking at the source code is a good way to understand the platform. Here we can see that this is the code with the incubate the replicant part, and we see the event prompt comes in. We capture the event prompt. We do a thing called initialize ledger. We won't get into that right now. Then there's initialize the state, which we had talked about the state holding the context. And once that runs, we call this this just state, where it means we are gonna. Some of the terminology of the names of the functions may throw you off, but it's to help with a paradigm. This is kind of a different paradigm than you can typically think of workflow stuff. But we just state. And if we can see the code below that, and the reason why that's broken out, because there are other places where this code can get called, specifically in your alfs. But we can see that we don't want to look at the first couple lines there. Really what we care about is the part where it will get the alf from the vault. And then it will do a called implant memory. And that is the part where I had spoken of that the alf definition, it will try to get it from what we call the vault, which is the in-memory cache, or get it from the depository, which is the on-disk cache. And then if it can't find it there, it will go to the depository that is on S3. So once it gets that, it calls the implant memory function of that alf. And then that is how everything runs. That will be running the activity, draw a conclusion, and move on to the next step. So if there was an indication that there was a malfunction when the replicant's trying to run its activity based on the alf definition, we would go and in that next catch, we would catch that and set the malfunction. And this is the function that sets the malfunction. You see, it's actually pretty simple. It sets a status, and we'll get details of more of what status means, but it sets the status as malfunction. That's what we would actually see coming back from the resolution. And then sets the conclusion, right? It says, oh, it's a malfunction, and it will always have these this malfunction of type, details, and trace. And so that captures whatever that malfunction was. And the malfunctions can be explicit or implicit. That means things that may happen from the runtime that are implicit, like a network goes down, there's something weird that we don't necessarily have a captured malfunction for. It will still propagate up through here. And then there are explicit malfunctions that are a part of the runtime, but also in your code, you can explicitly cause a malfunction. And a malfunction doesn't necessarily mean an error or an exception, but it can mean both. But it could also just basically means that the replicant couldn't perform the alpha activities for whatever reason. There was an issue with the runtime. So now the last step in the runtime flow is what we call the finally, and that always will run. So we always want to return a resolution, even if there's a malfunction or issues with the system. We always will try to turn a resolution. The code for a resolution is a little verbose, as we can see here. Part of the code here has to do with committing the long-term memory. If we want to, what we call notify or broadcast out. Well, we don't have to get into the details of that, but you can see that it actually happens around a try block, which means that there could be a malfunction that happens when you try to create a resolution. Now, in practice, that should never happen. That's by design. If it's happening here, that means there's some other catastrophic things happening, meaning network issues, whatever. And since you're running on AWS, most of this stuff should never happen. But we still do try it, so we can have a malfunction that would come back that makes sense. So you can see at the top there, it creates a resolution and then does some things. And at the bottom, we return, get the payload and the resolution. So it returns back a resolution. Now, just for full clarity, if there was a malfunction happening at the resolution state, it will catch that malfunction and does a bunch of things to understand that malfunction. You can see the type, we call it Deckard fatal resolution. That means typically if this would ever malfunction here, there's something that's happening that's truly bizarre. It could be a bug, but in a perfect world, this code here would never run. And the platform is designed in a way that this should never run. But this is sort of the fail-safe. And the point of doing it this way is that it would still come back from the Lambda execution as an error, but it wouldn't be formatted in a way that is designed with how malfunctions are formatted. So we don't have to go into much of this code, just understand that it will capture that malfunction. So to summarize, the idea here is that the runtime, receives event prompts. It's an event prompt processor. From that information in the event prompt, it will incubate a replicant, which is, you can think of it just running code, right? Some of the terminology here is just to change a paradigm of thinking. And from that, after a replicant has performed an activity defined in an ALF configuration, it will reach a conclusion. And the conclusion may involve a malfunction. But that said, the runtime now will emit a resolution that involves conclusion information, status, and genealogy. And the way the system is set up is pseudo-async. And that'll make more sense as we look into actually running some code. But this was a high-level overview, and as we go into the next training video, we'll actually start looking at ALFs, the definitions of those, and looking at code and running a ALF or incubating a replicant.